然后请你先加一个就是西队的，然后这场地对这场地切需要去哪里？就是接旧场那边的场地，排球有4张。没事听到。4次。
这听不见。
Okay, good afternoon, everyone. So before the beginning of the talk, so I believe so many of you have already heard the sad news. So the great Professor Lin-Chin Liang left us yesterday. So please allow me to borrow you 15 seconds. So closing your eyes to memorize the great Professor Lin-Chin Liang for 15 seconds. Thank you very much. So now it's my honor to introduce you, so Professor Pavel Propa. So Pavel, so he did a bachelor study in the Western Australia University for mathematics and physics, and then he moved to University of Cambridge, so Trinity College, for a PhD degree, and then he moved to Heidelberg University for a postdoc, and then he became a professor at Kiel University in Germany. And then, so now he's a professor at University of Bonn, and I believe that's a joint appointment with Charles University in Prague. And so Pavel, he is very famous for his work on the Senate initial mass function, so which is actually the application. So it's a work with a tremendous application in the study of the lambda CDM cosmology. So people use it to create a Mach catalog in the cosmological simulation to try to mimic the observational galaxy catalog. And interesting, so Pavel himself doesn't seem to agree with the lambda CDM model, so actually he's against it. So today, so he will tell us what is the reason he's against the lambda CDM model. So let's welcome Pavel.
Thank you, and a great pleasure to be here. Thank you for this opportunity. The lambda CDM model is a great model. It's accessible to computations. That's a great advantage, and it is claimed to have many successes. Now, if it's a good scientific theory, it must be testable, which means it must have predictions which can be tested against observations. And this is what I have been doing since quite some time now with a few people who work with me. And I will explain to you the consequences of these tests. Can you hear me? Yes? Good. So the issue is detecting dark matter. As you will realize, dark matter is essentially the central pillar of the lambda CDM model, of our current understanding of how the universe evolved and how structures came to be and how galaxies formed. If dark matter doesn't exist, this whole this whole theoretical body collapses, and we are left with nothing, in the sense of we wouldn't be able to understand at the moment how the universe evolved. And so testing for the existence of dark matter is indeed a very central issue of current theoretical and experimental physics. There's a huge effort to try to detect dark matter particles, to verify the existence of dark matter particles. So far it's been negative, and I want to explain to you how one can do astronomical tests, which are comparatively very cheap, and they have been done, with the consequence that there is an issue with the existence of the dark matter. And so First, as a note, as a preamble, we want to remind ourselves that the standard model of particle physics, which includes quarks, leptons, the exchange bosons, does not actually offer any path to an additional particle, which could be the dark matter particle, right? This MOP is actually a very good model in the sense that it seems to be an excellent description of what we see around us. And theoretically, in principle, we would be able to calculate from the few particles which define the standard model of particle physics, the existence of a tree, the DNA, and so on. In principle, we could do that. Now, it's also important to note that none of the experiments find anything beyond the standard model of particle physics. There are a few tensions here and there, but the model so far has been verified very well with the highest energies accessible to us for now. Now, the Large Hadron Collider does constrain extensions of the standard model of particle physics, in particular supersymmetry, which has been developed in order to accommodate dark matter as well as some other issues. But the dark matter particle was thought to be perhaps supersymmetric particles of the known particles, right? So the problem is that the expectations from the supersymmetric models have not been found, and this is a quote by George Redlinger and Paul de Jong. The beautiful theoretical ideas underlying supersymmetry have not been seen in nature, at least not in the simplest form we expected. So one would, if one wanted to still keep investigating this, move away from the more natural, simpler supersymmetry formulations. And it's important to remember that the only single argument for dark matter is the astronomical one. It's based on extrapolating a law of gravity to scales on which it was not defined. So as a physicist, you will know that from experiments, you can derive a law from a series of experiments, and that law, which you might extract from the data, for example, a fitting function to some to some data, if that should not be extrapolated. Or you can extrapolate it, but you would not expect the extrapolation to work very well if the extrapolation goes very far. Now, what is being done in astronomy is that we have the law of gravitation being defined experimentally on the scale of the solar system in the 17th century by Newton. And when Einstein reformulated this in terms of a space-time curvature, he used the same data essentially. There were no additional data available at that time except maybe 1 or 2 planets in addition in the solar system. And so the law of gravitation, as we know it in terms of Einstein's formulation or the classical Newtonian formulation, is an empirically based law, essentially, defined on a scale which is given by our solar system, because when Einstein wrote down his general theory of relativity, galaxies had not been discovered. They were not known to exist. The astronomers knew about nebulae in the sky, but it was not known what those nebulae were. And not even the scale of our Milky Way was known. And so the application of Einsteinian gravity to scales beyond the solar system is an extrapolation of an empirical law, and applying this to the scales of galaxies and even to cosmology is an extrapolation by a very large number of orders of magnitude. And so obviously any physicist, at least a well-educated physicist, will immediately deduce from this extrapolation that is most likely not going to work. You can still use it as a formulation of your theory, but always with a hindsight or with the expectation that this might actually not work. And so the failure of the extrapolation is what we need, is the basis for the introduction of dark matter. It can be the prediction of new matter, dark matter, or it can just be the failure of the extrapolation. The question is which is more likely and which one is correct. So There are a number of reasons why astronomers and physicists like dark matter or believe in dark matter. The most important one is that we have a well-developed Einsteinian theory of gravitation, which is believed by the majority to be correct. And I'm saying believe, which is a non-scientific term, because that is actually what is happening. Yeah? But one really, if we speak about dark matter, it is associated, it's a synonym with a belief that the gravitational law we're using is by Einstein. But it's an unscientific word. A scientist should not actually be using the word belief. Now, rotation curves of galaxies are flat, and this is solved by introducing dark matter. That's an important empirical motivation. Stars in satellite galaxies move too rapidly. Again, one can introduce dark matter to solve that problem. If you only use the visible matter with Newtonian gravity, the galaxies would fly apart. So you need extra matter to bind them. The mass of the local group of galaxies and of galaxy clusters, again, is too small in terms of what we see. The galaxies are moving too rapidly relative to each other, and the galaxy clusters would fly apart unless we put in additional dark matter, if we think that gravity is described by Newtonian law of gravitation. The cosmological model based on this theory needs extra matter to account for observed quick structure formation. So this is an important argument, and it's independent of the arguments I've just said. And this is a reason why many physicists and astronomers are convinced there is dark matter, because you have very different types of arguments. The one is the motions of matter in galaxies, and the other one is how the universe evolves and creates structures. If we would calculate the model of the universe after the Big Bang without dark matter, no structures would form. Galaxies would simply not be able to form because the baryons have a too low density, and they would just disperse through the expansion and would not be able to form structures. Furthermore, the cosmic microwave background radiation, so the CMB, is explained by this theory. The first prediction of the CMB was actually in a cosmological model without dark matter, and that was the first correct prediction for the first and second peak in the power spectrum. But then later measurements showed that the subsequent peaks did not match, but the dark matter cosmological theory had never made a prediction. They only post-fitted the observations. Okay, so that's an important little technical detail. So we have the standard model of cosmology, the SMOC, and it's based on Einstein being valid, and another very important assumption, that is that all matter is created at the Big Bang. That's a very important assumption, which is usually not stated, but it is one of the most important assumptions, including the first assumption. And so based on these two assumptions and the introduction of dark matter and then dark energy, we have a model which can be calculated. So the model begins with the hot Big Bang, an inflationary epoch, and then the expansion. As the universe expands, the baryons, the gas cools and falls into the dark matter halos, the potentials formed by the dark matter particles, making structures. And today we observe the universe as we see it with galaxies. And now a new phase of inflation is beginning, which is driven by so-called dark energy. A problem with this model is that inflation is physically not well known, dark energy is not well understood, and dark matter has not been found. So the standard or concordance cosmological model consists of about 70% dark energy. Dark matter comprises 25%, and baryons only about 5%. Now the problem with this is that this is what we expect in the model. We have only found about 40%. Most of the matter which supposedly was created with the Big Bang, in terms of normal matter, has gone missing. It's thought to be between the galaxies in an unobservable form, yeah? But that's an assumption. And so uncomfortable with this model is that the dark matter particles are not part of the standard model of particle physics, which otherwise is a very good description of the known observable universe. They have not been experimentally verified at all. despite a very, very significant research effort worldwide. And also uncomfortable is that the dark matter particles have not been found. Yeah. So these problems are uncomfortable. They are not a falsification. So we can still assume this model to be correct. We note these uncomfortable points, but this is not the basis for arguing that the model is wrong, because the model is very well defined by the equations which are used in the calculations. And contra, which actually now falsifies the model, are a whole number of tests one can perform. So basically, since we have a mathematical model which can be used to do calculations and therefore predictions, we can test these predictions against observations. And every single test and predictions I've seen and have been involved with has failed. I honestly do not know any single prediction, truly a prediction, not in the word of the cosmologist who uses prediction as a postdiction. If you look at the papers, that's the way it's explained. The written, we predict, but actually it's predicting, calculating something which has already been observed, so it's not a prediction. The word prediction means you predict something before it is known. And every single case I know of where a true prediction has been made has always been falsified by observations. And this is just a small list of all these problems. And they rely on one essential physical process in physics, in gravitational physics, and that is dynamical friction. Dynamical friction due to the dark matter halos that should exist in the above theory is simply not detected. And associated with that, as a sort of sub-points, are all these other points. And I will be addressing these 4 points, but I will start introducing this here. And so I will go through them in turn. And these are only 4. There are many others I could have kept going. I could speak for 3 and 4, 5 hours explaining each test made and why it is a failure. Okay, now, so a direct test of the existence of dark matter particles is dynamical friction. So Chandrasekhar dynamical friction. It's remarkable that the physics community is not using this test to detect or falsify the existence of dark matter particles because it is completely cheap. You do it, and it has been done, and we know whether dark matter exists or doesn't. Now, dynamical friction works, it's very simple. Yeah, you have a galaxy moving through a halo of dark matter particles. These are dark matter particles. And the dark matter particles interact gravitationally with this galaxy, and they are deflected on their orbits and make a overdensity behind the galaxy. And loosely speaking, this is not the correct physical description, but loosely speaking, this wake of dark matter overdensity behind the galaxy attracts the galaxy backwards, decelerates the galaxy, and the galaxy comes to a stop or falls towards the center of the dark matter halo, and therefore merges with the galaxy. This can be calculated. This is very straightforward. We have here the galaxy. This is the dark matter particle which comes in on this trajectory, and the dark matter particle is deflected along this trajectory here. So it changes its velocity, initial velocity vector from this to that. And in the center of mass coordinate system, this means that the galaxy itself makes the reverse motion. But it's very small because the dark matter particle could be an axion, which is an incredibly small mass, or it could be a WIMP with a larger mass, but it's much, much smaller than the mass of the satellite galaxy. And so the satellite galaxy reacts to the interaction with a single dark matter particle in an incredibly small manner, in such a way we wouldn't be able to measure it. However, there are an incredibly large number of dark matter particles. And so what happens is that we can calculate that the deflection, so this component of the final velocity vector comes in from this equation. This is just a solution to the conic sections, the Kepler problem. It's nothing else. It's exactly the same you have in the solar system, planets moving around the sun. So there's a hyperbolic orbit around the gravitating body. This deflection can be calculated with this component in the change of the velocity vector, and this component being that change of the velocity vector of the dark matter particle, which is reflected by the motion of the satellite galaxy in the center of mass frame. And this is from Benin Tremaine, by the way, this figure, so you can read up on this. It's very, very basic physics. And so this can be nicely calculated. Of course, this deflection depends on the impact parameter, so the distance of the dark matter particle from the galaxy, and the velocity, as well as the mass of the galaxy and the mass of the dark matter particle, which is completely negligible, of course, compared to the galaxy. So we can calculate this, and then what we have to do is for each single encounter, we know this deflection, and then we have to sum up all the encounters. So the galaxy is moving through a sea of dark matter particles, and each encounter we can calculate, and then we have to sum up all the encounters to find the final effect on the velocity of this galaxy. Now, these components cancel out because there's a dark matter particle coming from that side and a dark matter particle coming from that side being deflected upwards. And so the galaxy is moving through, is deflected this way, and this way, up and down, and ultimately it cancels out. But this component adds, you see, it's always in one direction. And that's the origin of Chandrasekhar dynamic friction. The satellite galaxy moves through the dark matter halo, becomes slower, and ultimately it will stop. So the addition of all these encounters leads to this acceleration or deceleration of the satellite galaxy. This is the famous dynamic friction formula. It depends on the velocity of the satellite galaxy and on the mass density of the dark matter halo. So it depends on the mass and the number density, but together it's the mass density. So the mass of the individual dark matter particle is not important. It's the mass density, and that is constrained by cosmology. You cannot tune this. This is an untunable number because we know how much dark matter must exist in the lambda CDM model for it to be consistent with a hot Big Bang and structure formation and dark matter halos. Right? So this is a factor we cannot play with, and therefore this is a solid prediction of the motion of objects in dark matter halos. Now, when the satellite galaxy is on a circular orbit within the host galaxy, then dynamic friction exerts a torque. So we have now a galaxy, it's surrounded by a dark matter halo in the theory, and the satellite galaxy comes in and moves in this dark matter halo and is decelerated, which means its orbital angular momentum perpendicular to the orbit is changing, so it's being torqued. This is the formula for the change of the angular momentum with time. That's the torque, and this is how it's calculated. For a circular orbit, these two are at right angles. The radial position vector is at right angle to the dynamic friction force, which goes backwards, and so we can calculate how a galaxy loses angular momentum and sinks towards the center of the dark matter halo as a consequence of this dynamic friction. So the angular momentum, we have these equations. You see this is the dynamic friction force. That's the deceleration here. And that's the angular momentum of the satellite. So this can be calculated and solved. And that's the time it takes for the satellite galaxy to sink to the center if it begins at this distance in a dark matter halo in which the dark matter particles have a velocity dispersion of this number. For example, our Milky Way has a dark matter halo with a velocity dispersion of 200 kilometers per second, approximately. And this is the mass of the satellite galaxy. This is just a Coulomb logarithm, which is of order of about 10. Now, galaxies merge once they approach within distances comparable to the diameters of the dark matter halos as a consequence of this. This is what this means. You have two galaxies that come to each other. Once the dark matter halos touch, dynamic friction essentially becomes active. The galaxies lose kinetic energy, and therefore they must fall towards the potential center and merge. That's why astronomers today believe that all galaxies form through mergers exactly because of this process. But they can only do so if dark matter exists. Otherwise, they do not merge. Okay? So, for example, if we take a galaxy, a satellite galaxy with a mass of 10 to the 11 solar masses, in a dark matter halo like our Milky Way with 200 kilometers per second, so this is kilometers per second, is equal to parsecs per million years, starting at a distance of 200 kiloparsecs. We have the Milky Way, a satellite galaxy at 200 kiloparsecs, that's basically the edge of the dark matter halo. It will sink to the center of the Milky Way within only 1 billion years. Dynamical friction is incredibly effective and efficient in merging galaxies. So we know the properties of these dark matter halos from the theory. As I said, we have a well-developed theory. It's a mathematical model, which is why I like it. I'm not against the model. I'm scientifically testing for the existence of dark matter. And as a scientist, if I conclude it doesn't exist, then that is my conclusion. I stand by it. So we know the properties of these dark matter halos. And this is the mass of the galaxy we observe. So for example, our Milky Way has a mass up here of a few times 10 to the 10 solar masses in gas and stars. And according to the theory, its dark matter halo has a mass of a few times 10 to the 12 solar masses, maybe 2 times 10 to the 12 solar masses. That's our Milky Way up here. A satellite, a dwarf galaxy with a mass of 10 to the 6 solar masses in gas and stars, and such galaxies exist, would have a dark matter halo mass of about 5 times 10 to the 9 solar masses. And these are various models, so there is a dispersion because the history of each galaxy is different, depends on how the dark matter halos merge to make a particular galaxy. So a galaxy with a given number of stars and gas will have a slightly bigger or smaller dark matter halo depending on its exact history of formation, and that's why there is a scatter. So there is a scatter in the expectation, but it is well defined in the sense that we know it's not here or here. So we know the mass of a dark matter halo of a galaxy we can observe. So for example, a 10 to the 8 solar mass pre-infall satellite galaxy ought to have had a dark matter halo mass more massive than 10 to the 10 solar masses, such that its orbital decay time would be short. So here's, for example, our Milky Way seen edge on. That's the bulge of the Milky Way. And it has 2 major satellite galaxies. This is the large imaginary cloud, and this is the small imaginary cloud. This one is at about 50 kiloparsecs from the center of the Milky Way. This one's about 60 kiloparsecs. Both are moving past the Milky Way, and each of these has a very massive dark matter halo around it, if the theory is correct. This one has a mass of about a few times 10 to the 11 solar masses, which is nearly 1/10 of the mass of the Milky Way dark matter halo, and this one is about maybe 1/5 or so of the mass of this one. So both of them are orbiting about each other, and they should be sinking relative to each other through dynamical friction. And the whole system, as it's orbiting the Milky Way, should be sinking towards the Milky Way, and this is not observed. What we observe is that both of them are old, and they haven't merged, but they're very close to each other, only about 20 kiloparsecs, which means they are sitting within the dark matter halos, and they haven't merged yet. So it must be a complete coincidence that they came past our Milky Way just before they merged. Furthermore, we know that the velocity of both galaxies is far too high. Both galaxies came in from a large distance, and they came deep into the dark matter halo of our Milky Way to 50 kiloparsecs, and they're going past on a basically hyperbolic orbit. This is physically basically not possible unless one gives them a very large initial velocity, and then the question is this consistent with the velocity field of the cosmological model? Now we know, we know very well the dark matter halo masses, and we know how big these dark matter halos are. So for example, if we have a dark matter halo of our Milky Way, which is about this mass, that's the mass of dark matter halo, then it has a radius of about 250 kiloparsecs, according to the theory. And a dark matter halo of the LMC, which would be around this mass, would have a radius of something like 150 or so kiloparsecs. So these things are huge. Remember that the LMC is sitting at 50 kiloparsecs away from the center of our Milky Way. Our Milky Way has a dark matter halo with a radius of 250 kiloparsecs, and the LMC has a radius of 150 kiloparsecs, and the SMC, which has a dark matter halo mass around this point of 50 kiloparsecs, is sitting in its dark matter halo, and all these dark matter halos are on top of each other. So the system, this 3-body system of dark matter halos, should be merging like mad, and we just don't see any evidence for that. Now, dark matter halos are like a spider's web. Once a galaxy approaches a dark matter halo of another galaxy, it's captured irreversibly and will merge. This cannot be undone. And here's a simulation of two galaxies with dark matter halos, and you can see how they interact, and the centers now merge. You see? They merge because there is dark matter. You can also see that energy and angular momentum conservation throughout these tidal tails, which have a certain length. But when the galaxies merge, the potential energy is created, and this is compensated by kinetic energy, which has to be expelled. And this is what these tails do. They expel the kinetic energy, but they have to climb out of the dark matter potential, so they can only get to a certain distance. And it has been noted some time ago that the theoretical tails are much shorter than the observed tails. Here are now real galaxies which are encountering each other. An astronomer believes they are merging. The correct formulation is that these galaxies are encountering each other. These two galaxies are encountering each other, and these are also encountering each other. You see the names up here. This is the famous Antenna Galaxy, the beautiful tidal tail. And this is a galaxy which people think has already merged. It might just be strongly encountering and then moving apart. So we can calculate exactly these cases, which has been done by this group, Pivon, Barnes et al. In 2013. So this is the separation of the galaxy against time. For example, here's the Antenna Galaxy. It started in the computer at this distance as it's observed, and it merges. So they approach each other, then they separate, and then they merge. The same with the other galaxy, like the mice. They start, they approach each other, they separate a little bit, and then they approach each other, separate a bit, and then they merge. In all these cases, if there is dark matter, they merge within 500 million to about 2 billion years, depending on the initial conditions. So they merge much more quickly than the age of the universe. So this is very well understood. Already in 1998, Barnes wrote that the dynamics of galaxy interactions, that interacting galaxies are well understood in terms of the effects of gravity on stars and dark matter. So basically, we don't have a mystery here. This is very well computable, calculable, and we know the timescales involved. And so this can now be applied to the dwarf satellite galaxies of the Milky Way. Our Milky Way has about 40 satellite galaxies. At this time, these 4 satellite galaxies, called Fauna, Sculptor, Ursa Minor, Carina, had measured motion, velocity vectors. So we, at this time, only these 4 we know how far they are and where they are positioned, but to measure the motion is extremely difficult. Yeah, but this has been done for these 4 with these uncertainties, and so we can use these data, given their distances and their current velocities, to test whether dynamical friction can be active in these satellite galaxies as they orbit the Milky Way. Now note that they are far away. For example, Fornax is at 140 kiloparsecs, Carina is at 100 kiloparsecs, and these other twos are at distances larger than 70 kiloparsecs. And they are moving quite fast. You see, they're moving at velocities comparable to 200 kilometers per second, despite being very, very old. These are very ancient galaxies, basically as old as the globular clusters. And they are at large distances and moving very fast. This can only be possible if they fell in recently, because otherwise they would be at the center of the Milky Way and not at these distances. And so we went backwards in time, given these conditions, we calculated them backwards in time to see where they could have come in, and we find no tenable set of parameters for these 4 galaxies. And today this can be done for many more satellite galaxies, because with the Gaia mission we have many more and much, much better measurements of these motions. And this is a project which is actually now undergoing with a student in Mexico who visited Bonn for 2 months. And we started this project, so we will do these calculations, including many more satellite galaxies, to further enhance our understanding of this problem. But the thing is that if we assume there's dark matter, therefore dynamical friction must be active, we don't find solutions which are physically reasonable for the motions of these satellite galaxies, because they should be decaying, but we don't see them decaying because they're simply at too large distances. So we can then look at the the next group of galaxies. So we have the local group of galaxies where our galaxy is a member and Andromeda, and the next group outside is what is called the M81 group. It's at a distance of about 4-5 megaparsecs. This 3.6 megaparsecs, and it's therefore the closest group to our local group, and therefore we have good data on it. The further we go away, the worse the data get. The CMB is the most distant object, and therefore it cannot be the most critical constraint on any theory. It's simply the most distant object we have. Here we have the closest group, and so we can study its properties. This is what it looks like. So we have here the main galaxy, M81, that's like Andromeda and Milky Way. Then we have the next galaxy, which is a little bit less massive than our Milky Way. And then we have this galaxy and this galaxy and this galaxy. So we have 1, 2, 3, 4 galaxies plus these clouds. There are other dwarf galaxies there too. Now, these are very substantial galaxies. So it's a more complicated system than our local group. And what we see from this gas distribution, so this is a hydrogen survey around this group, what we see here is that these galaxies have been profusely interacting because the gas has been scattered everywhere in the group. One can do simulations of this to see how the gas is dispersed after encounters, and this can only be done actually if there are multiple encounters. So here is an optical image of the group. This is what we see with our human eyes if they were sensitive enough. And this is a previous radio image of these 3 galaxies, where we already saw how the gas is distributed and that these 3 galaxies must have had encounter. Now remember, dynamic reflection is very effective, which means that these 2 galaxies would merge in something like 2 or so billion years. These 2 galaxies would merge in something like 2 billion years. The fact that we see a system here of 3 galaxies, and in fact actually 4 galaxies, which haven't merged, means that all these galaxies must have come together less than 2 billion years ago, which is an incredible fine-tuning because you have the universe expanding, you have 4 galaxies, and they for some reason decide to deviate from the Hubble flow, fall toward or fly towards each other, and just at exactly the same time, cosmologically speaking, they come together, they have an encounter before they merge. And we just see it at the point where they came together before any of them have merged, because all of them are well-defined this galaxy, so none of them have had a major merger. This is so finely tuned and contrived that it's basically impossible to have happened. And so it's interesting that some time ago there was a contribution by Jung, 1999, who looked at the dynamics of the systems, and there are no solutions with dark matter. He only found solutions without dark matter to this distribution of matter and the fact that they haven't merged yet. This was a conference proceedings, and it was never published in a refereed research paper. The question is why not? Now, independently, an American team did the same calculations, but completely independently, and they found exactly the same result: no solutions with dark matter, system merges, unless one takes away the dark matter. Again, at conference proceedings and no refereed paper. So we thought that we would address this issue and try to publish a refereed paper on this problem, and that's what we did. Wolfgang Oehm is he's a PhD in physics, theoretical physics, and he went to industry and got bored, and in his free time he approached me to do research, and I suggested, why don't we do this? And that's what he did. So he's independent. His livelihood does not depend on his reputation in the field. So he was free to lead this research, and this is what we did. And this is the results. So basically, we did manage to publish it. We had to take out some statements out of the paper, otherwise it would not have been publishable. But basically, all members of the M81 group would have to have fallen in synchronously from large distances and have a perigalactic encounter with M81 at nearly the same time without having merged it. So this is so fine-tuned that the likelihood of this happening is ridiculously small. It's difficult to calculate the likelihood, but you will see that this is a huge problem. Now, if this were the only group, maybe one could live with it. The problem is that there are many similar groups. And that's what kills the theory, right? So we have, for example, here, what are called the Hickson compact groups. So we have 1, 2, 3, 4 major galaxies. So 1, 2, 3, 4 major galaxies of the mass of the Milky Way sitting so close together that they're basically a few radii away from each other. And they are very old galaxies. Some of them are reddish already because by encountering each other, the gas is channeled to the center or expelled. They go through starbursts, they consume the gas. And so today we see mostly an older population of stars, and the current star formation rate has been suppressed because the gas is basically gone. It's either at the center or expelled or used up, but they haven't merged. So we know from the properties that they've gone through many encounters, but they have not merged. And then there is a large number of these in the nearby universe. Now, one could consider that these groups are merging and then they form an elliptical galaxy and new groups form all the time. The problem is that the merger product, which is the elliptical galaxy, doesn't exist. We do not see the equivalent elliptical galaxies which should form from these mergers in the field. Therefore, the conclusion is that they cannot be merging. And so the present-day motions and distances of Milky Way satellites preclude them to have fallen in from a filament. If they have dark matter halos, the M81 group should not be there. And so there's no dynamical friction due to dark matter halos. That is the only conclusion which I can draw. I'm not asking you to draw this conclusion, but definitely this is a conclusion I very strongly draw based on this evidence. And so there can be no dark matter halos. So we can now say this is a conclusion. There's no dark matter halos, but as I said before, the conclusion is profound, because if there's no dark matter, our entire understanding of cosmology falls apart and we have nothing. And so we want to be sure this conclusion is correct. Therefore, we want to do other tests which are completely independent or largely independent of this. And so this would be the phase-space distribution of matter. How is matter actually arranged compared to the model with the observations? And so what you see here, what we know from the theoretical model, this is the merger tree, is that at the Big Bang, which is up here, so when the universe was very, very young and was expanding, the gas was a plasma and very hot, and was completely smoothly distributed. But the dark matter particles don't interact electromagnetically, but they interact gravitationally. And so the dark matter particles don't see the baryons because they're completely smoothly distributed, and they start gravitating among themselves because there's slight density fluctuations in the dark matter distribution. So dark matter particles make the first halos, and as the universe expands, these dark matter halos merge, making bigger dark matter halos. And as the gas cools, the gas starts to fall into these dark matter halos and starts making the first stars, galaxies, and more dark matter halos emerge. And this is what this shows. These are the first dark matter halos, the little ones. They merge to make bigger dark matter halos, which merge to make even bigger ones, which merge to make even bigger ones. And today we see a Milky Way or Andromeda here with this huge dark matter halo around it. And each galaxy has such a merger history in that model. And each merger history is different. It's like a fingerprint, which is why the galaxy should be quite different from each other rather than being very similar, because every galaxy has its individual merger history. But there's an important prediction from this. And the prediction is that the mergers are random, and every galaxy has a different merger history, and therefore the dark matter satellites ought to be distributed spheroidally. So we have a galaxy like the Milky Way, and its dark matter halo is basically round. It's not completely round, it's triaxial, but it's basically spherical. And the dark matter satellite halos in it, which come in and slowly merge with the galaxy, are distributed just like that. They're basically spheroidally distributed, isotropic. This is a very strong prediction and has been tested to death. We've looked at every single calculation basically ever done, Millennium, Illustris, Eagle, and so on. Anything you can get your hands on, this is exactly the statement, which is completely rigorous. you cannot distinguish the distribution of the dark matter subhalos or the satellite galaxies which are in these subhalos from a truly isotropic distribution with a significant level. But the observed galaxies are not isotropically distributed. And so this is what we expect. This is dark matter in a negative way. So these are dark matter halos. They come in and they orbit and slowly lose orbital angular momentum through dynamical friction until they merge. The big ones do it more quickly, the small ones much more slowly. The big dark matter halos should have satellite galaxies. In fact, the prediction was that each such galaxy, like our Milky Way, should have hundreds, if not thousands, of satellite galaxies, because each of these dark matter subhalos, which are merging with this dark matter halo, bring in satellite galaxies, but we observe only about 40. So there's more than an order of magnitude discrepancy, and this is called the missing satellite problem, which sort of is solved by saying that most of these small ones simply made stars which blew out the gas and destroyed the galaxy. Okay, that's a particular attempt. But this does not touch on the prediction that those which survive as satellite galaxies must be essentially spheroidally distributed around the Milky Way. That's a very, very firm prediction. And this is what it looks like. So here we have now Andromeda. This is 500 kiloparsecs on each side. This is the disk of Andromeda galaxy seen edge on. And all of these are satellite galaxies. And what Ibata et al. Have found is that there is this plane of satellite galaxies. It's very thin and huge in extent. So we have Andromeda, and there's this plane of satellites which are orbiting in one sense. So these are going towards, away from you, and these are coming towards you with some interlopers. There's evidence for another plane of satellites, although this is not so significant because there are not so many. And this could be a plane which is seen inclined. But this plane is extremely significant, as shown in this paper, in a Nature paper here. Now, the Milky Way galaxy has an even stronger anisotropy. So this is the Milky Way disk seen edge on. Again, the system of satellite galaxies is a disk which is quite thin. It's about 20 kiloparsecs thick, 250 kiloparsecs in radius, and it's rotating. So these are going towards you, these are going away from you. Today we have more points. This is established even firmer, but all of these parts are empty. This structure is highly significant. If you do calculations of how statistically significant this is, very, very significantly different than isotropic distribution. Furthermore, these satellite systems are correlated. So we have here, we are now looking from the top of the local group. This is the Milky Way disk in black, and this is Andromeda disk here in black. And so this is now a scale of nearly a megaparsec across. And if you look from the top, we see the disk of Andromeda satellites is this one here. That's this disk. And the disk of Andromeda of Milky Way satellites is this disk. And both of them are rotating. Now, this disk is aligned exactly with the Milky Way. This one is offset by some, 30 or so degrees. But both of these disks of satellites are rotating in the same sense, which means that these satellite galaxies and these satellite galaxies are correlated with each other, which is physically impossible in the model, because in the model, this galaxy formed independently to that galaxy. And this has been tested again to death by Master Pawlowski. He looked at cosmological simulations, selected dark matter halos, which are in pair, like these two. This dark matter halo has a radius about this radius, this one about this radius. He selected such pairs of dark matter halos and looked at the satellite distribution and found that they have no correlation whatsoever. There's no correlation between these pairs, satellites of the pairs of dark matter halos. So this correlation is statistically very significant, and it shouldn't be the case in the model. So how can the Milky Way and Andromeda satellite systems be so correlated if they are subhalos falling in individually? This merging history is different to this merging history, so they should not know about each other. In Lambda CDM, they can never have had an encounter. If Andromeda and Milky Way had come closer to each other, they would have merged a long time ago. So they can never have They must have been completely independent. So after the Big Bang, they're separated, they're formed, and now they're coming together in the Lambda CDM model. Now, in this paper by Müller, Pawlowski, and in Science, they looked at Centaurus A, and this is the title page of Science, a cosmological conundrum, because they showed that the next galaxy, so we've heard of the M82 group, and just a little bit further in another direction is the Centaurus A group. It's again like the local group, but a bit more massive. And that galaxy, Centaurus A, which is somewhat more massive than the Milky Way, has a large number of satellite galaxies. And they discovered by observation that this satellite system is incredibly correlated. It's a thin plane of satellites. We are looking at it edge on, and it's rotating, which means we can measure the radial velocity. So we know that the system is beautifully rotating. And so we now have the situation that the Milky Way and 31 planet of satellites are not unique. In fact, we have 3 such systems. So we can look at an attempt to quantify this probabilities. Assume lambda CDM structure formation, and we can ask the question, how often should we find such disks of satellite systems? The Milky Way has a probability of about 10 to the minus 6.6 times 10 to the minus 3 if we use the Millennium-2 cosmological simulation as quantified by Pawlowski. This is a very conservative estimate. It's actually much smaller if we take into account also the fact that it's a rotating disk of satellites, which is not part of this calculation. So this is actually a much smaller probability. We are being very conservative. The likelihood that the Andromeda has a disk of satellites as is observed is 1.4 times 10 to the minus 3 relative to Millennium-2 cosmological simulation. The likelihood of that Centaurus A has the disk of satellites as observed around Centaurus A is 10 to the minus 3 relative to Millennium, or 5 times 10 to the minus 3 relative to the Illustris. If we now put this together, combined, we see that the probability that 3 of these relative to Millennium is 10 to the minus 9, and here is 10 to the minus 9 relative to Illustris. This basically means that we expect, based on these calculations of the cosmological structure formation, we expect to have to look at 240 million galaxies to find 3 cases with satellite systems similar to this, remembering that we are using very conservative quantification of the disk. It's much, much worse. What we actually have in the real universe is we look at the 5 closest Milky Way type galaxies, and 3 of them have these disks of satellites, and it's those 3 which have been observed. The other 2 have been observed yet. Which means that these disks of satellites are the rule, not the exception, while in the Lambda CDM model, they are the complete exception and completely unexpected. So, so this is more than a 5 sigma falsification of the theory, based on a different argument than the dynamical friction argument. Now, in the standard model of cosmology, structures form from many independent stochastic mergers. So you saw the merger tree. So every galaxy has a dark matter halo, which has its own merger history, and it's a stochastic construction of all these mergers. We expect no ordered structures in the theory. The local group, where we have the very best data, in the local group, we can put the galaxies into 3-dimensional space because we have the data. This is lost further out because we don't see the relative distances well anymore. Here we have the distances very well. So what we're looking here at is now a dimension of 3 megaparsecs times 3 megaparsecs. We are looking along the line of Andromeda Milky Way. So Andromeda Milky Way are sitting in space with their satellite systems. And we are now looking along the line of Andromeda and Milky Way. And you can see here the crosses are the satellite systems of Andromeda and Milky Way. And all these other galaxies are galaxies which belong to the local group, but are not satellite systems, are not satellites. And you can see that all of the other galaxies in the local group are on 2 thin planes, 50 kiloparsecs thick, 1.5 megaparsec in radius, in extent roughly 1.5 to 2 megaparsecs in extent, symmetrically arranged around the line of Andromeda Milky Way. So we have the situation that we have the line Andromeda Milky Way, and then we have one plane of galaxies and another plane of galaxies. It's like a roof. It's equidistant from the line joining Andromeda Milky Way. And all the galaxies in the local group are either around Andromeda Milky Way or in these two planes, and everything else is completely empty. So this here is totally empty, empty, empty. These are the motion vectors which we know of. So based on radial velocities, they are consistent with the galaxies moving in these planes. This structure is a Hubble time old. It's as old as the universe. How can it have sustained itself for 10 billion years without these galaxies falling to the center or orbiting through? If you set up such a system in the computer and you evolve it for 10 billion years, it is physically completely impossible to keep the structure, because these galaxies would either fly out, move through, and this symmetrical structure would be lost within a few billion years. You would never be able to detect it, but it's 10 billion years old and it's still there. What does this mean? This is why I call this the frightening symmetry. It looks like a crystal in a sense. Matter where we can measure the positions of the galaxies to the best accuracy is arranged in a highly unexpected symmetrical manner. And this is completely not understood in any theoretical model. Now, the structure of the local group galaxies is incompatible with the standard model of cosmology. In fact, currently it's incompatible with any known theory. Because even in a non-Newtonian theory, I would not know how to create such a structure and sustain it. Now, the thing is, if you go beyond the local group is that region in space which decoupled from the Hubble force. After the Big Bang, the universe expands, and little regions which are over-dense collapse from self-gravity. And those regions have a zero velocity surface where the matter is basically not moving outwards and not moving inwards, and inside the galaxies are bound. And so the zero velocity surface of the local group is about like this. And if you now look beyond the local group, there are 5 galaxies which are in a plane, 50 kiloparsecs thickness, 1.5 megaparsec in extent, parallel to one of these planes and moving away at about 200 kilometers per second. So we have the situation that we have the local group with Andromeda Milky Way, these 2 planes of galaxies, and beyond it is another plane of galaxies which is moving away from the local group. The thing is, it's the scale. The scale is a megaparsec or more than a megaparsec, and they're all moving together synchronously away from the local group. It's in step, like soldiers moving away, in step. And then how does one make this? 50 kiloparsecs thick and more than a megaparsec across. Now, if you calculate them backwards in time, 8 billion years ago they were in here, which means 8 billion years ago they must have been ejected somehow. But how do you eject a structure of that dimension outside of the local group, which is structured with potential wells and has dark matter in the model? And how can you eject these galaxies, which they themselves have huge dark matter halos? It's physically impossible. This analogy is, which I like to bring up here, is to say that if you're underwater and you take a rock and you try to throw the rock up, it doesn't work. You can't expel the rock from the water. You throw the rock up and it comes down. That's exactly what would happen here. You try to expel a single galaxy outwards and it would just stop and come back because of dynamical friction. But they're moving well beyond the local group at unbound velocities, and they're moving in step together as if they had not known that this potential existed, and this potential is made of 2 big galaxies, right? So on that scale, there's a 700 kiloparsecs distance now, and the structure which has to be ejected is on a 1.5 megaparsec scale. And how do you eject such a system so that all the galaxies are moving at the same velocity, basically, in a thin plane outwards from such a two-body two dark matter halo system? Physically completely impossible. Now, this is called the backsplash problem because it has been noted that getting such high velocities is impossible in lambda CDM because you can't eject galaxies out of dark matter halos with these velocities. But the problem is much, much worse. It's not just the backsplash problem, it's the synchronization of the ejection out of potentials where if you move at slightly different velocities, and because you're climbing out of a potential, you simply change your velocities and then their positions. And so that is really a seriously huge problem. And the fact that this is parallel to one of these planes. So what the hell is going out on in gravitation and the local universe? Now, the backstretch problem is that there are too many galaxies are receding from the local group too orderly in a plane and too fast. This is impossible. The local group has dark matter. Dynamical friction would slow capture the galaxies. And so the consequences of random mergers are that the disagreements concerning tests relying on dynamical friction and the distribution of matter are consistent with each other. So this is very important. You see what I'm doing here. I'm making one test and then doing another independent test. And what we could have had is that one test is negative for dark matter and one test is positive for dark matter. Then we'd have to think a bit harder about the tests. But the point is, each of these very careful tests are consistent with each other in negating dark matter. There's no disagreement between the tests. And they always and only point to dynamical friction not being active. And this can only be the case if there are no dark matter halos. And so the final point I want to bring up is, again, an independent test. And this is referred to the dual dwarf galaxy theorem. In any cosmological theory, there exist primordially formed galaxies and tidal dwarf galaxies. So there are two types of galaxies. In the Lambda CDM model, primordial dwarfs are dominated by dark matter and tidal dwarfs have no dark matter. So this allows us to test. So this is again the simulation. We see the two galaxies interacting, merging because they have dark matter, and these tidal tails which form. You see here new galaxies form. And this is just a consequence of standard physics. So the tidal tail expels, it's gas-rich, the gas dissipates energy, forms these dwarf galaxies. And we know that these dwarf galaxies cannot contain dark matter because the dark matter particles are moving around too fast and they cannot be captured in these galaxies. And so, and this is an actual image of the real galaxy where we see exactly this happening. So this is just that these things are happening in reality. These are called tidal dwarf galaxies that form without the help of dark matter, while the primordial galaxies form with the help of dark matter. And so, at the same baryonic mass, they must have different radii, because the one galaxy forms in the potential of the dark matter halo, so with higher pressure, and the other galaxy forms naked without the help of dark matter. And so this has been tested and it's falsified by data. And it's been tested in this paper here, where we looked at the illustrious simulation. We looked at the sizes of these galaxies which formed as tidal dwarfs. We've identified this all what Moritz Hasselbauer has done, an amazing piece of work. And they have different radii to the galaxies with dark matter, and both of them are inconsistent with the observed radii of galaxies. So this independent test verifies the previous conclusion, dark matter does not exist, because what we observe is that both these galaxies, these types of galaxies have the same radii. The Lambda CDM model predicts them to have different radii, and both of the radii actually do not agree with the observed radii. Right? So therefore, this is now the end. Dark matter halos do not exist. Cosmological model ruled out. Well, that is the only sensible conclusion. If I'm not driven by dogma, as a scientist, I must not be driven by dogma, then this is the only allowed conclusion I can draw. And so, interestingly, in this paper by Václav Vavričuk, which was published by Monthly Notices of the Royal Astronomical Society, he showed that if you take the dust between galaxies and you add up all the flux from the dust at cosmological distances, you get the CMB with 2.77 Kelvin, which shows that if there is dust between galaxies, and we know there is dust between galaxies, then that dust emission at large cosmological distances contributes to the CMB significantly, if not wholly, and this wipes out the CMB as a cosmological evidence for the hot Big Bang. And so the conclusions is that it seems the observed universe does not contain dark matter. By implications, the standard cosmological model is not the correct description. the observed universe appears to be more regulated, have more symmetric structures than expected. And how to proceed? We look at galaxies and their properties to build up a new model. And so this is what we are now doing in Bonn. We are now seeing whether we can, from the observed galaxies, infer new laws of nature, which we might then be able to use as a basis for some attempts towards a new cosmological model. So thank you.
Thank you very much. We can take one or two quick questions because at HIF, so we have the talks in 5 minutes. So.
I have a comment and a question. I have a comment and a question. The comment is that your conclusion that there's no dark matter is probably too strong. You should have said no cold dark matter, because the wave dark matter can lead to dynamical friction that you have a log lambda, right, in the dynamical friction formula. Log lambda is 0.5, 0.6, so it's not 10. So that would prolong the dynamical friction time. And a question is following. You see this sort of large scale planar structure, and would it be pancake collapse?
Well, no, because a pancake collapse would work if you'd have one plane. The problem is that we have two planes inclined, so you'd have to collapse from very small regions, but then Y into two planes which are symmetrical around Andromeda and Milky Way, and then we have the other plane just moving away, right? So this, I wouldn't see how this would be possible.
But the plane can move in any direction. It doesn't need to be symmetric.
The problem is that the age of these planes, they are too old. So for some time we could imagine could create some planes, but they would then deform because of the gravitational field, and so we don't see that. Right? And so that is a problem. Yeah, concerning fuzzy dark matter, I agree that it affects the calculation of dynamical friction on say kiloparsec scales, but it wouldn't affect the fact that the galaxies form through mergers, because dynamical friction is still active, just on a somewhat larger scale, and you still have mergers. And so the distribution of satellite galaxies, which is on a scale of hundreds of kiloparsecs, would not be affected. I mean, it would still be wrong in the theory, I'm afraid. You know, I'm not. As I really want to emphasize that I really do think that the dark matter hypothesis is an important hypothesis, but it's just not what the universe is doing. That's what I have to conclude.
But your argument is entirely based on, or largely based on dynamical friction, and now the dynamical friction is much smaller than what you estimate.
Well, I don't think it's much smaller. The scales, well, you still have to form structure in the fuzzy dark matter halo, and so fundamentally you have to have the same type of structure formation. Otherwise, you don't get the more or less agreement with the number of galaxies per unit volume, because you form galaxies from the mergers in this model. There's no other way to do it, and so dynamical friction must be about as active, maybe a little bit less. But the question is whether then one can actually show that you get the type of galaxies which we observe, and galaxy clusters. So if one reduces dynamical friction, then one gets into problems of forming galaxy clusters quickly. And we know from observations that galaxy clusters appear at a high redshift, massive galaxy clusters appear high redshift, which is already now in tension with lambda CDM because it's not even doing it quick enough. And so any change in the dark matter particle would be a problem in that sense. I'm very convinced, personally, very convinced that the path with dark matter is simply not the correct path. It is the wrong path.
So any other really quick questions? So maybe we leave to NDF people.
Okay, I also have one comment and one question. Well, first comment is about you say the dark matter is not realized in a standard model. That's true, but why particle physics still very interesting? Because standard model itself has a lot of problems. For example, neutrino is not massless and the strong CP problems. If you try to solve lots of the problems, the particle they introduce automatically satisfy. So that's the reason why particle physics still exciting. But second is my question is about your analysis about do you have a statistically, because early this year Joe Silk has published he showed there's a mechanism to make this satellite galaxies is dark matter free. So in that case means that once you have dark matter, you can find something has a dark matter, something without dark matter. So do your analysis has some statistically tell us how much even fractions? How much fractions? Because in your argument just 1 and 0 with dark matter and without dark matter. Is it not possible to tell us about how every dark matter positions within these systems is maybe only 2%, 3%?
Yes. Now, concerning your first point, I completely agree. The theoretical physicists should concentrate on understanding the standard model of particle physics and its deficiency. The theoretical physicists should not be motivated by trying to include dark matter. That is completely the wrong way, and you will not get a successful theory by doing that. But yes, the tensions which exist in the standard model of particle physics, they have to be sorted out by theoreticians, including understanding antimatter. Interestingly, we know antimatter exists, but there's little research on it as far as I know. Now, considering the second point, yes, we know that there are, so any lambda CDM cosmological simulation makes dark matter free galaxies and galaxies which have a little bit of dark matter. And we know why this is the case. In fact, we wrote the most sophisticated paper exactly on this problem. This is Moritz Hasselbauer et al. And the reason why the model fails is because the radii of these galaxies with dark matter and without dark matter, which form in the lambda CDM model, are wrong. I mean, they are correct in the model, in the calculation. They do depend on the baryon physics, but that's why we can use Eagle versus Illustris versus Fire simulation, which is very different baryon physics, and they're all wrong. And so the radii are wrong compared to the observations. And so this doesn't help. I mean, in terms of saving the model, the likelihood of getting a dark matter free model in the dark matter calculations is very small. Only many of them form, but they are transient. So the galaxies merge; they form short tidal tails, not the long ones we observe. Short because of the dark matter halos, and the galaxies which form in these are then destroyed by tides in these strong fields. While in reality, the tidal tails go much further out because there's no dark matter, and the satellite galaxies which form, they keep orbiting for Hubble time if they form very early.
Okay, thank you very much. I think we should close this event now. So let's thank the speaker again.